Welcome to this section on the course on Introduction to Measure Theory, and this section is titled Lebesgue Outer Measure. In this section, we shall define a set function which will serve as an extension of the Lebesgue function, and that particular set function is called Lebesgue Outer Measure. Lebesgue Outer Measure Amster of a subset A of R is defined to be the infimum of the sums of lengths of countable classes of open intervals whose union cover A. From this definition, we usually have the following informations. First, Amster, the outer measure of the empty set, is equal to 0. We can easily confirm this with the help of these arguments, because the empty set is contained in the interval minus epsilon to plus epsilon for every positive number epsilon. So, by definition, Amster of empty set is less or equal to S epsilon, and because epsilon is any positive real number, therefore we must have Amster of empty set is equal to 0. If A is a singleton set, then Amster of A is 0, and the outer measure Amster is monotonic. That is, Amster of A is less or equal to Amster of B if A is contained in B, where A and B are subsets of R. Here the results can have a problem. Please give justifications of the last two statements. The outer measure is actually an extension of the length function. Here we establish this proposition: if I is an interval, then Amster of I is equal to length of I. We give a part proof the result. In fact, we shall prove the result for a closed and bounded interval AB. So, if I choose a positive number epsilon, then the open interval cover A minus epsilon, B plus epsilon contains only one member, and so Amster of I is less or equal to the sum of lengths of this open interval cover, which is equal to B minus A plus 2 epsilon. And because epsilon is arbitrary, we must have Amster of I is less or equal to B minus A. On the other hand, if epsilon is any positive number, then we can use Haine-Borel theorem to show that Amster of I is greater than or equal to B minus A. So, from 1 and 2, we have Amster of I is equal to B minus A, which is equal to length of I. The next proposition says that the outer measure Amster is translational invariant. So, if I have an open interval cover In for A, then In plus x, where x is a real number, is an open interval cover for A plus x. And therefore, Amster of A plus x, by definition, it is an infimum of the sum of the lengths. So, it must be less or equal to this particular sum. And because length of In plus x equal to length of In, so we have this particular equality. Therefore, Amster of A plus x is less or equal to Amster of A. Now, if I replace A by A minus x and then x by minus x, we have Amster of A is less or equal to Amster of A plus x. So, from these two inequalities, we have the required result. Next, we state a proposition which is called countable subjectivity of outer measure. We omit the proof of this. This says, if we have a countable collection of subsets of R, then Amster of the union of the countable class is less or equal to sum of Amster of ANs. From this proposition, we immediately have this important corollary. It says, if A is a countable set, then Amster of A is 0. The proof of this corollary follows like this: if A is a countable set, then we can arrange its members in the form of the sequence and then we write A as a countable union of singleton sets, AIs, where AI contains small ai. Now by countable subadditivity, M star of A is equal to M star of union of these AIs, and this less or equal to sum of M star of AIs. And because these AIs are singleton sets, so their outer measure is 0. So M star of A is non-positive. But M star of A is already non-negative, so we must have M star of A is equal to 0. We state another property of outer measure with a proof. Suppose A is in subset of R, then for any epsilon greater than 0, there is an open set O which contains A, and M star of O is less or equal to M star of A plus epsilon. Further, there is a set Z in Z delta such that A is contained in Z and M star of A is equal to M star of Z. Now the obvious question is Lebesgue outer measure countably additive? For time being, we leave this question unanswered and move to the next sections for further informations. We finish the section by pausing 2 questions per readers. If I is an interval, then prove that M star of I is equal to length of I. And if A is the set of natural numbers and epsilon equal to 0.01, then try to find an open set O which contains A, but M star of O is less or equal to M star of A plus epsilon. Thank you.